Hi, welcome to the lectures on topology. We are going to talk about what are popularly known as countability axioms or properties of topological spaces. For me, there are three things which are somewhat worth mentioning. They are known as first countable, second countable, and separable. And believe me when I say that, you just have to learn them and just work with one or two examples to understand what they are. Okay. In my opinion, only second countable space are very important for analysis as well as modern topology, because they always deal with second countable, locally compact Hausdorff spaces. The underlying structure is this. If you don't know about locally compact, forget it. We will come to that later. Okay. And whereas functional analysis, they will always keep saying about separable Hilbert space, separable Banach space, or some such thing. Okay, these are the only times when you come to know about those things. Okay, but traditionally in the points of topology course, all these notions are always given. So it's worth learning basics, and okay, don't get worked up too much about that. Okay, if your aims are different kind, but if you're obsessed with points of topology, of course, okay, no problem, you should work more on that, you should also learn more on that, but I'm not the person to learn from. Okay, you have to look at some classical books like Dugunji, Willard, Pervin, Kelly, and so on. Okay, there are also some German books, I don't remember, but you have to. Okay, don't be discouraged. Okay, what you are going to do will be something very, very useful and substantial, okay, for your course. So let me write down all the three definitions together, right? So let X tau be a topological space, right? So I say X is first countable, that is X tau. Okay, remember the tau is already X is first countable. Yeah, maybe I should say, okay, let me say, if for every X in X there exists a collection B Xn, where n is a natural number, of open sets such that X belong to Bx. Okay, let me drop these things. Okay, for all n, and there is a collection with what property? With the following property. Yeah, maybe no, let's forget it. I'll come to the definition later. Okay, I'm sorry. Somehow I'm very reluctant to give this lecture apparently. Okay, I'm kind of resisting this. That reflects in my way of doing things. Okay, suppose X is a metric space, right? Now for each X we have this collection Bx 1 by n. Call it as Bxn, right? So this collection Bxn as n where is, what property does it have? If U is open and X is in U, then there exists an n in n, so that Bxn, that is Bxn, is contained in U, right? So the picture is like this. So for each X I have various kinds of open sets like that. Okay, these are all my Bx 1 by n's. Okay, so I have a countable family. Okay, look, so do you see that in some sense it's not a basis for all of the topology, but for the open sets containing us, it's a basis. What does that mean? If you give me an open set U containing X, then I can find an element bxn so that bxn is contained in u. Remember, bxn always contains x. Are you following? Okay, so this is one example to keep. Okay, the second example to keep in mind is, let us look at R with usual topology, right? Then let's look at Q. Let's look at Q, and for each R in Q and natural number n, we have this collection R minus 1 by n, R plus 1 by n, as R varies over Q and n is over natural number. This is a countable family. Okay, and this is also a basis for the usual topology. We had already seen when we talked about topology, basis for a topology, we had already seen this, right? So what is the importance of this? Okay, here you can see I have a countable family of open sets, which is a basis. That is, I have a countable basis for the topology. In the earlier case, in the metric space case, what did I find? I find that for each x there is some kind of local basis. Okay, I will define it in a minute. And the third thing is again R, okay, with usual topology, or R with lower limit topology. Also, we know that Q is dense in R usual topology, also R with lower limit. These are all already seen. Okay, so that means there exists a countable dense set. Right, these are the three examples you should always keep in mind when you talk about countability properties or axioms for a topological space. Okay, I am going to say your topological space x tau. Okay, I am going to say a topological space x tau is separable if I can find a countable dense set, as we did in R. R with usual topology, the set of rational numbers is countable dense set, right? And when you come, the second thing I'm going to say, a topological space x tau is second countable if you can find a basis which is countable, basis for the entire topology. Okay, and first countable, okay, requires a little more care, as I explained in the case of metric spaces. We will define that also, right? Okay, so let us go back. So let me do the ulta thing. Okay, let us go backwards. Okay, x tau, okay, then x tau is separable if there exists a countable dense set. So the examples R with usual topology and Q, or R with lower limit topology with Q, right? Okay, and of course any countable set with any kind of topology, okay, that will be separable. Can you see that? Take x to be any countable set, I don't care what topology you keep on that, but that will be countable dense set, because x itself will be the dense set which you want. Yeah, okay. Now I say x tau is second countable if there exists a basis, there exists a countable basis, let me say. So what does it mean? That is, there exists a countable collection Bn, n in n, Bn to open sets, so that for every u in tau, u is going to be union of some subset of this group B. Okay, so every element can be written as a union of basic open sets. There's a record. Again, typical example is R, and what is the basis I have? Just now I wrote it, R minus 1 by n, R plus 1 by n, where R is in Q and n is a natural number. This is a typical example. To define the third thing, let me first make a definition. Let X tau be a space and fix a P in X. Okay, a collection B P I varying over indexing set. This indexing set also may depend upon P. Okay, is a local basis at P. If what are the things I should have? P belong to BP of I for each I, and 2 for each I BP of I is open. Third, if U is in here and my P belong to U, then there is an I in I of P, so that P belong to BPI, that is contained in U. Okay, again if you want, instead of ball I just have to write it. This means this is my X, then this is my UIP. These are my UPIs, and therefore if you give me let me say, if you give me an open set U, okay, containing P, I should be able to find one from this set BPI, so that P belong to BPI, and that's containing this. So what is the typical example? A metric space. Yeah, very good. Okay, now when do you say a space is first countable? If there exists a countable local basis for each P in X. So if I want to write it carefully, as I usually do, is first countable. Okay, if for every P in X there exists a countable local basis. So in the case of XD, what is the countable local basis? For each P I am going to take this. Is that clear? So please stop, go through the definition. Remember, the basic trick here is to look at the three typical examples I gave. For first countable thing, remember a metric space, and at each point X, then look at the open ball Bx 1 upon n as n varies. That is a local base. For second countable, what do you need? You want a basis for the entire topology which is countable. What is the typical example? Our R or Rn for that matter. R. What are the things there? R minus 1 upon n to R plus 1 upon the open intervals, with R varying over all rationals and n varying over natural numbers. And separability now talks about, not those two things talked about something to do with the base and topology, open sets, whereas separability talks about density. So I say a space is separable if it has a countable dense set. Okay, Please go through it, keep that in mind, keep these 3 examples. Once or twice you revise, then you will see all the concepts are very easy. So let us look at some easy examples. Okay, of course, first examples are okay with the usual topology. Then what do I know? I know this is first countable because it's a metric space, and it's also second countable. This was a motivation example, and it's also separable because Q is dense in R. Right? So this is the easiest example. Now let's look at any metric space XD. So what do I know? I know it is first countable because this was a motivating example for this, right? And I want to know whether it's second countable, and I also want to know whether it is separable. Suppose I take X equal to R, that is uncountable set, with a D equal to discrete metric. Okay, then this shows that it's neither second countable not separable. Why? Because you look at this singleton X, okay, this family has X square is over X, or here it's R, okay, these are all open sets. So if I have a Bn, a countable basis, suppose Bn is a countable basis, okay, right? Okay, now look at this X. This is an open set, X belong to this. Since this is a basis, that means what? There is an n equal to n of X. Okay, so that X belong to Bn of X, and that is contained in singleton X. What does that mean? That means B n of X must be singleton X itself, right? You understand that? Yeah, right. Now do you see a problem? Because if X is not equal to Y, okay, then this Bn of X is not equal to Bn of Y. Please go through it. This is very easy, but this kind of thinking is never encouraged. You just say, you believe, you accept it as you accept religion. Okay, that's a problem. Remember, science is not religion. You have to ask questions, you have to justify everything. Okay, what did I do? Look at this, an open set, and since this is a basis, there is an n, so that X belongs to Bn and Bn is contained in this. But X is already there. That means singleton X is contained in Bnx, and Bnx in turn is contained in singleton X. That means these are equal. Therefore, so for each Bn, okay, I have done that. Okay, now if X and Y are different, then Bnx and Bny will be different, right? But the set of X as where X varies over R, that is uncountable, whereas your Nx has to vary only over set of natural numbers. Okay, that's countable. So this contradiction shows it's not second countable, right? And it's not separable. So pause, review, proceed. Why it's not separable? Suppose D is a countable dense set. Right? Then D is not equal to R. It's a proper subset. Therefore, R minus D is not empty. Call it U. Since we are dealing with a discrete space, discrete metric, okay, this is an open set, right? And non-empty. And since D is supposed to be dense, what do I know? U intersection D should be not empty. But I know this is already empty because U and D are complement to each other. Yeah, therefore it's not separable. Have you understood? Okay. So let's look at such a simple example. Okay. Now let's look at R with lower limit topology. Right? Okay. Now what do you think I should do? What are the basic open sets? You know, basic open sets are like this. Okay. Closed at A, open at B, where B is greater than A. These are the basic open sets, right? Very good. Now, this is first countable because for each A in R, I can look at this set A plus 1 by n. This is a local base at A. Because any open set containing, suppose A is an open, A belong to U is in tau L, okay. Therefore, that means there exists a basic open set A comma B which is contained in U, right? Now B minus A is positive. Therefore, by Archimedean property, because these are the things which are never explained in topology course, okay, analysis. So by Archimedean property, this must be greater than 1 by n. There exists n, so that means B is greater than A plus 1 by n. Therefore, if I take A plus 1 by n, that is contained in A, B, that is contained in U, right? Therefore, I have proved this is a local basis. Okay, and we know it is separable. We know Q in R tau L is separable, is dense. Okay, in fact, when I talked about density, I pointed this out. This is something very strange because tau L is finer than tau, the usual topology. So if a set is dense in a topology, certainly it will be dense in any topology which is coarser than the topology tau. But if tau dash is finer than tau, then there may exist a non-empty open set U in tau dash which may not intersect the given set, right? Therefore, it's very rare. Okay, you should not expect, right? Okay, but in this case, it turns out even though tau L is finer than tau, the usual topology, Q is still dense in this. Therefore, this shows that R tau L is separable, right? So I have seen lot of wrong intuition. One expects if x tau is first countable and separable, then it is second countable. Intuitively, because you look at R and Q, okay, this is separable, therefore I have Q. Then what do I look at? I look at R minus 1 by n, R plus 1 by n, because first countable, so I use it. Okay, one usually thinks first countable and separability should mean this is wrong. That's why I said wrong. Okay, the typical example is this. So R tau is not second countable. Okay, why? Suppose Bn is a countable base. Right, now let's look at any A in R. Right, let us look at the basic open set A to A plus 1. This is a basic open set, right, containing A, right? So what do I know? I know there exists an n equal to n of NA, a natural number, so that A belongs to Bn and Bn is contained in A to A plus 1. Right? Now something very interesting. Again, my favorite thing comes. Okay, you have to understand GLB, LUB. Okay, now let's look at that. What is the GLB? of a to a plus 1, of course a, right? And remember again, this is very basic things about if a is a subset of b. Okay, these are all subset of R, assume they are non-empty. Okay, what is the relation between GLB of a and GLB of b? Okay, because remember, if alpha is greatest lower bound for b, alpha is less than or equal to x for all x in b. In particular, alpha is less than or equal to x for all x in a also. Therefore, it will be a lower bound for a. Therefore, but GLB of a is the greatest lower bound. Therefore, what do I know? This is must be there. I already gave you quickly. Okay, pause, review. In case you have not learned these things well, I just went through the proof. Pause, rewind, and play this. Right, now my Bn is already contained there. Therefore, what do I know about GLB? GLB of Bn should be greater than or equal to a. Right? But remember, is contained in a. Bn is contained in a to a plus 1. Therefore, for each x in a, you know that x is greater than or equal to a. And a also belongs to this. Therefore, a is actually a minimum of b. Minimum of b as well as it's a minimum of a to a plus 1. This is b and a. Bn of a, I don't remember what I wrote. Anyway, I wrote earlier, it's a b n a. Okay, whatever. Is that clear? Now, the argument is exactly similar to what we saw just above earlier. This similar argument is what I am going to use now. Okay. So, for each a in R, okay, let us look at the map R going to this. A going to the GLB of B and A, which is A. Right? You understand? Okay. Right. And if A is not equal to B, this is a 1-1 map. You understand? Right. But remember, GLB of Bn as n varies over this is a countable set. Because for each Bn, I can talk about GLB, and that is going to be, okay, a real number, and that's going to be finite. Countable. So this is a countable set, whereas you are saying you have a uncountable set. Are you following? Please go through. Okay, pause, review, proceed. So this contradiction shows R with the lower limit topology is not second countable, though it is first countable and separable. Please keep this in mind. I have seen few experts, okay, intuitively feeling just because of R and Q, this must be a true statement. The first countable separable space must be second countable. That's not true. Okay, now let's quickly look at one or two things about these are the two standard results you will need in my life. These are the things I usually, if at all I needed these things either in analysis or in functional analysis or in sometime in topology. That is, if I give a metric space xd, okay, this is second countable if and only if it is separable. Okay, we will prove that. Yeah, but this way is clear. That is, yeah, okay. See, more general result. Okay, if x tau is a topological space and assume x x tau is second countable, then x tau is separable. Okay, this is a very easy theorem. Okay, suppose Bn is a countable basis. For tau, right? And notice that when I say Bn, it's an open set. There is no guarantee, you know, if some Bn may be empty, but then that doesn't serve any purpose. Do you understand that? So if you intuitively believe Bn may not be empty, but that's not the case. Okay, I may be mischievous. If you give me, for example, if you give me r minus 1 by n, r plus 1 by n, r in q, and n in n, this is the basis, countable basis for R with usual topology. I can take union empty set also, right? This is still a countable thing. It's a countable collection of open sets, and it's a basis, no problem. Do you understand that? So, but this serves no purpose. Having an empty set in a basis serves no purpose, right? So we can as well assume Bn is different from empty. It's not empty for all n. Okay, very good. Now since Bn is not empty, now let's look at that. What I want to prove? I want to prove it's separable. But what does that mean? That means I have to find a countable set. Then I have to prove its dense. How do you think I will prove I will get a countable set now? That should be easy, because I already said Bn is, I am assuming for each n Bn is not empty. Therefore what should be the set? Yes. So choose and fix one element xn in Bn. Fix a point in Bn, call it xn. Now let's look at D equal to Bxn. N in n. Okay, this is a countable set without any trouble. Again, be careful, we are not claiming for n and m different, xn and xm are different. They could very well happen. Okay, these are the things intuitively many people assume lots of things, but you will see it doesn't matter to us. Okay, for x10 I would have chosen the same point, x29 also I might have chosen the same point. Okay, so when I collect the collection, this double point will go away, only one will remain. Are you following what I mean? X10 and x29, so one of them, as I said, okay, I can keep only one. Are you following? Okay, so I claim D is dense. Why? Suppose you use a non-empty open set and tau, right? Since it's non-empty, there exists an x in u, right? Now since u is open, x is in u, and Bn is a basis, though what do I know? There exists a natural number n so that x belongs to Bn, and this Bn is contained in u. You see that we are using the part use non-empty to collect an S, and we are using the part Bn as a basis to collect a Bn, right? Now xn belong to Bn by our construction. See, remember, for example, I would in my earlier thing, my x10 will serve for, suppose x belong to B29 and B29 is contained in u. Remember, the point x29 chosen is nothing other than x10. Therefore I will take x10 here, right? So there is a xn which belong to Bn, but of course it belong, right? And it belongs to D also, because xn is in D. But this is a subset of what? Bn is contained in u, therefore u intersection D. Therefore xn belong to u intersection E. Therefore it's not empty. So D is dense. Okay, pause, review, proceed. So let's go back. What did I prove? I wanted to prove if you give a metric space, it is second countable if and only if it is separable. But what I said is, one way I don't require X to be a metric space. For any topological space, if it is second countable, it is separable. That's what I proved. So the converse, we'll assume now XD is a metric space. and which is separable. So I want to know whether it is second countable, right? Okay, so where do I find it? Yeah, so now contrast this with respect to what we did earlier. Let us look at R with the lower limit topology. What did we know? It is first countable, it is also separable, but not second countable. We proved it, right? So here, yeah, XD, a metric space, is of course first countable, but it has a lot more thing. It is a metric space. Okay, so we have to make use of that. Now the proof works. Okay, now what will I do? So it's separable, therefore let D be the countable density Xn, right? Maybe call it Xk, K in here. Then I want to produce a basis. Now remember, how did I prove in R with usual topology? Take R minus 1 upon n to R plus 1 upon, that is B R 1 upon n, as R varies over the countable density, right? So that's the same thing. So what we are going to do, we are going to look at Bxk 1 by n as k varies over n and n varies over n. Okay, this is a countable collection of open set. That's very clear, right? Because each open ball is an open, and this is indexed by n cross n. N is countable, therefore n cross n is also countable, therefore this we know is countable, right? So we want to claim this is a basis. It's a basis. It is countable, is clear. Okay, so I want to show it's a basis. What does it mean? You give me an open set U in the matrix topology, let X belong to U, right? Then what is that I have to do? I have to find a K and N so that X belong to B, Xk 1 upon n, and that's contained in U. This is what I have to do. Right? How am I going to do that? I'll work backwards. Those of you who had been following my videos, you know I always do that. Instead of giving a textbook proof, I always work backwards. Suppose such a thing, suppose such, okay, assume K and N exists as above. Right? So what is it I have to do? Give me any y in Bxk 1 by n. I have to say it is contained in U. Right? So keep the picture. This is, oh, okay, this is my, let us say, U. Okay, right? Now I have an X. So this is, no, I don't want this. Let me just, I don't like it. Okay, so this is my X. This is my open set U, and this is my point X, right? You understand that? Okay, now what is that I have to do? Go back. What should I show? You have given a point X in U, then I have to find X belong to this and that, right? So I have to find a Bxk 1 by n, right? So how do I do that? The first thing is X belong to U, U is open. I know there exists an R positive so that Bxr is contained in U. Yeah, this is my Bxr. Yeah, now remember Bxr is non-empty open set and my D is dense. What is D? D is Xn, right? Yeah, D is dense, right? Therefore, what do I know? I know there exists a K such that xk belong to BXR, right? So let us try to estimate. So let's try to estimate dyx. This I know is less than or equal to distance between y and xk plus distance between xk and x. But I want to make sure this is less than r, because I want to say y belong to BXR. So you understood that? So what I have is, I have an open set which is containing this. Okay, and whereas the center may be something else. This is my xk. I have to find. I want to show this less than r, right? Now what do I know about distance between y and xk? That is less than 1 by n, because I still have to find an n, right? Remember, my xk, y belong to bxk 1 by n. Therefore distance between y and xk is less than 1 by n, plus distance between sk and x is less than r. Okay, now how do I do that? Okay, if you have learned analysis properly, you will know what to do now, right? Remember, D is dense in xd. Therefore, okay, if I choose n such that 1 by n plus 1 by n is less than r, then I'll be okay. Then what will happen? Let us look at bx 1 by n. Okay, this should intersect D, right? Therefore there is an xk there. Are you following? Don't worry, I am trying to think aloud. If you are getting confused, I'll give you textbook proof. Okay, yes. So what will happen? So the distance, so now let's look at the textbook proof. Okay, let r be such that bxr is contained in u, right? And next choose n a natural number so that 2 by n is less than r, right? Now I claim bxk 1 by n. Okay, yeah, sorry, this I choose 1 by n, right? Now look at bx 1 by n. Okay, this intersection is not empty, so let xk belong to this. Yeah, now we want to claim bxk 1 by n is contained in u. Now remember, xk, distance between xk and x is less than 1 by n, therefore x belong to this, right? So to do that, to show this containment, let y belong to bxk 1 by n. Then I want to prove ds y belong to u, but I will actually prove y belong to bx 1 by n, bxr, which is contained in u. Yeah, that means I have to estimate distance between y and x, but that's less than or equal to distance between y and xk and plus distance between xk and x. Remember, y belong to where? Xk 1 by n, therefore this is less than 1 by n. And this one, what? Remember, how did I choose my x? That's less than 1 by n. Yeah, but now how did I choose my n? That's less than r. Therefore for all y in b xk 1 by n, y belong to bxr and contained in u. So this means x belong to bxk 1 by n, that is contained in U. So we have proved this collection bxk 1 by n as k varies over n and n over n is a countable basis for xd. What is xd? This is a separable metric space. So go through the proof. What the intuition said is wrong. That is, you may believe a first countable separable space must be second countable. That's not true. Lower limit topology on R is a counterexample. But on the other hand, when we looked at RQ, what it said is, in a metric space, okay, if it is separable, then it is second countable. For any topological space, any second countable space is separable. So only one thing remains in this thing, that is, any compact metric space is separable and hence it's second countable. That's a fact which is also often used in analysis. Okay, so that perhaps somewhere I will prove it, but believe me, if you go through these things well enough, revise twice or thrice, that's more than enough about thing. Okay, there is also some Lindelof property, etc. Anyway, if I kind of take enough enthusiasm, bring out enough enthusiasm, okay, I'll come up with those things also in the video. But what I find in my life is these things are more than enough, except only one more thing: compact metric space is separable and hence second countable. We will see that scene. Okay, I hope you enjoyed, and go through the last proof. Again, I worked backwards because of time constraint. I know I went a little too fast, but then textbook proof was proper. Yeah, enjoy.